Syzygy, episode 68, Birth of a Planet. And welcome back for another edition of the Syzygy podcast, still in socially isolated mode, which means I, Chris Stewart, am sitting here at my desk in my very small office in my house in York, and across the other side of the country is Dr. Emily Brunsden. Emily, hi.
Hello, hello.
Good to see you on the Zoom.
I've also been isolated, not just from you in York, but also I've been isolated at a lounge today because other work is happening in the dining room.
Yes, you look like you're in an actual room as opposed to a sort of dungeon or something as you normally do. So yeah, nice to see you again.
Yeah, we've decorated this room.
Nice to see you. We've been a little bit quiet on the podcast for the last little while. I think we only did one episode in the entirety of the last month, but I think that was because that live episode that we did kind of tuckered us out. That was it was a fun episode, but it was fairly exhausting at the time.
Cool.
It was great. So those of you who listened to that and tuned in, thank you very much. It's been really, really nice. But today we're back for some more astronomical goodness. Today we're talking about planet formation. And this is not just a theoretical thing. Emily, apparently a planet has been spotted in the process of forming around another star. What's going on? Give us the details.
Yeah, we've absolutely caught this planet in action being born, which is super, super exciting.
Now, is that a rare thing? Have we seen this sort of thing much before?
Well, we haven't had so much direct evidence for a planet being actually in the process of formation before. So much so we're not even 100% sure if this planet is still forming or only just formed like 10 minutes ago kind of thing.
It's kind of an interesting question, isn't it? It's one of those things in astronomy, because of the time scales, right? Astronomy happens on astronomical time scales, hence the name. And you sort of forget that we don't see this very often. Like, we see planets around us and we assume, well, they must have, glommed together at some point. But actually spotting one in the process of forming is a very rare thing. Okay, so let's wind it back a little bit. Who has spotted what where, Emily?
Well, this is a team led by Anthony Boccialetti and from the Observatory of Paris. And they published, this was in May, they published some brand new images of this newborn planet being formed. Now, it's a giant planet. And it's not so much that we've got sort of a photograph of the, beautiful, like you can imagine the giant planets in our solar system, Saturn, Jupiter, Neptune, etc.
Right, we haven't got a shiny new close-up of a big shiny planet. What have we got?
No, we haven't even got something that looks like a sphere.
Right.
But what we have got is we've got kind of a twist in the debris that's surrounding a star that's just been born. That is indicative that this planet is forming now.
Oh, okay. So we've got a shot of, like, there's lots of dust and gas and stuff surrounding a star, and we know that's where planets come from, right? You've got a star in the middle and lots of stuff swirling around the outside, and that stuff slowly but surely gloms together to make a planet. And there's a twist in this one. What is the twist? What does it mean?
Yeah, so basically, if you can imagine all this sort of disk material that's forming around the star, it's got lots of structure in it. And in particular, it's got lots of spiral-like structure. And when you look into the detail of that spiral structure, then you can figure out what the origins of that is. And if you do some simulations as to how a planet would disrupt and create more structures in this disk, then you get the observations that we're seeing. For the star.
Right, so that we're seeing the telltale sign of, if you had a big swirling, whirlpool of dust around this star, if there was a planet forming, it would probably disrupt that in the following ways. And hey, look, there's one. It's this little twisty squiggle in the middle of they're quite amazing pictures, aren't they?
They are beautiful, really, really nice pictures. I mean, you asked me just as we started, are these real?
Yes.
I was like, yeah,
they are real.
Picture.
It does sort of look a bit like, if you gave an artist the job of, hey, look, we need a picture for this story. We've got swirling gas around a star with a bit of a kink in it. Can you just come up with something? It kind of looks like it would be that. And you kind of, you pinch yourself to think, no, that's real. What we're looking at here is actually out there. It kind of looks like, I don't know, Satan's bathtub going down the plug hole. Like it's kind of a little bit scary looking, but beautiful and amazingly detailed. Absolutely amazingly detailed. Okay, so this has been taken by which observatory?
Well, the research is coming out of the Observatory of Paris, right. But the images themselves have been taken from a instrument called Sphere, which is on the Very Large Telescope in Chile.
Right. Okay. So tell us a little bit about that, because, I mean, the images are extraordinary. This star is a long way away, and the images have a lot of detail in them. So how do you do this? How do you spot a planet in formation in this way around another star? What tools are we using here?
Okay. So, well, we've first got to go all the way right back to basics as to why we can't see planets around other stars. At least it's very, very difficult to see them directly, right? We've talked a lot about how we find planets by looking at, for example, the very small changes in brightness of a star if the planet passes in front of it in a transit. We've talked about how you can use the Doppler effect to watch stars wobble when they have planets. You know, these are all indirect kind of measurements, right? There's very, very few planets that we have been able to actually go and take a photograph
of. Because they're a really long way away. That's a thing in space.
They're really, really
it's a
long way
away, and they're very small.
They're also very small. They're not very bright. That's a problem. But even worse, turns out they're right next to something that is incredibly bright.
Yes, incredibly bright, and typically much larger than them. So, yeah, that makes it really, really hard. Okay, so we need these other techniques that allow you to infer there's got to be a planet there doing the following things of the following size on the following orbit and so on. You can work backwards from the observations, typically of the star itself. But is that what we're doing here? Is that where these amazing images have come from? This is different, right?
This is different. This is different because in this case, what we're doing is we're getting rid of the star.
Ah, okay. Or just sort of sticking your thumb in front of it.
It is. So Sphere is actually an acronym. You might not be surprised to find out. It's a brilliant astronomical acronym.
Go on then, lay it on me.
All right, let's go for it. It's spectro, the S, polarimetric, high contrast. I don't know where this is.
Yeah, just leave out the C.
High contrast, yeah. Exoplanet research instrument. I don't know how the I became an E, but it just did.
There's an E
experiment.
in the word.
Let's call it experiment.
Yeah, okay. There's an E in instrument. You can't make an instrument without the letter E. I don't know. It's in there somewhere. Anyway, sphere, which is a bit of a tortuous.
So spectropolarimetric high contrast exoplanet research.
Right. Well done, everyone involved in coming up with that one. That was well worth the time. Sphere. Yeah. What does sphere do exactly?
So it's a type of instrument we call a coronagraph. Mm-hmm. And a coronagraph does kind of what you said. When you hold up your thumb, you can stick it in front of the sun, right, and block out the light. This is kind of doing the same thing. It's just doing it in quite a clever way. So we're not going out into space and putting, big shields up. I know this has been proposed to make artificial sort of blocking tools where you make a big shield and you go and stick it in front of a star to see the fainter stars or fainter objects that are behind
quite literally make a big thumb and stick it in the way of the thing that you're looking at to block it out. Okay, so it's not doing that. It's not using a physical blocker. Doing that.
So, or at least it's only doing that right in the center, because the problem is that when you do observations from Earth, of course, it's hopeless doing that because the atmosphere bends the light around these kind of things anyway.
Right. Okay. Yeah. So that's not going to work. That's only going to work. If it's going to work at all, it'll only work in space. And that's a fairly expensive proposition. So, all right, dump that. What do you do instead?
So what you do instead is do something very, very clever. And that's use the polarimetry, which is the polarimetric part.
Okay.
Right. Now, polarization of light is kind of it's the direction of the electromagnetic vector that a photon has. So a photon is a wave, and it waves between electric field and magnetic field, and that has a direction. Yeah, it has a direction. It has a polarization, and so what you can do is you can block out particular polarizations of light. And indeed, this is what sunglasses do, right?
Yeah, your Polaroid sunglasses will block out anywhere up to half of the light coming through them, which is the electric fields or the magnetic fields wiggling in a particular direction in space. And it'll just block out half of it, which means you get less light coming through to your eyes. That's how they work. It's very clever.
Yeah. And sunglasses are really, really clever, really, because what's happening is the light from the sun, what you get is unpolarized, meaning the polarization directions are just random. They're
It's all over the shop.
Kind of, all over the place. Whereas if you get a sunlight that then bounces off something, so say a body of water, then that light becomes very slightly polarized, right? And it becomes polarized your sunglasses are actually polarized in the opposite direction, so they block that light. So they're preferentially blocking reflected light, which is glare. And so that's why Polaroid sunglasses work so well.
Yeah, designed to cut out the glare. Okay, so that's polarization. This technique that Sphere is using polarized light. How?
So similar concept, actually. So the starlight coming from the star is unpolarized, so it's going everywhere. But when that light goes into this disk, so as the star is forming, it's got this disk, as you say, debris, it's sort of dust and gas, the stuff that didn't make it into the star from its original cloud of gas when it collapsed. But when the light from that star goes out into this disk, it becomes polarized. So what we can do is use the fact that the reflected light is polarized and preferentially observe that to observe the disk, which would otherwise be way too faint to be able to spot.
Right. So it is actually a little bit like having a decent pair of Polaroid sunglasses, that it's cutting out the glare and leaving behind the other stuff. It's very clever.
It's very, very
okay,
cool.
But here's a question. How is it? I'm not understanding something. The light's coming out from the star, which is in the middle, right? And it's going in all directions, and it's unpolarized, right? So its direction of wiggle is random in orientation in space, yeah? It goes out in all directions, and it's interacting with the material around it, and that slightly polarizes the light. But aren't you still getting that polarization happening in all sorts of different angles because the light was going out in all different angles to begin with? Like, how do you choose what direction to put your Polaroid sunglasses at? Here on Earth, glare's typically coming from things which are horizontal or vertical. We can sort of choose that because we have a horizontal or vertical, but there isn't a horizontal or vertical in space. So how do you choose? How does that work?
Yeah, well, so what happens is that when that light gets absorbed into the disk and re-emitted, which is what's happening here, and we're looking in the infrared, right? So this is light from the sun goes out into the gas and dust and gets absorbed and re-emitted. But when it's re-emitted in a preferential direction. And that's based on the properties of the re-emission. A lot of it comes from the dust that's present. Dust is responsible for a lot of polarization in the universe generally. And it's one of these pesky things that interferes with other polarization measurements. One way you can imagine it works is that if you've got a dust grains are not quite spherical. They're kind of elongated. And what happens is that when dust grains sit in magnetic fields, they all line up the same way because of the magnetic field that they're experiencing. So that when you have light then interacting, it turns out that when it's re-emitted, it's all kind of polarized in the same direction.
Right.
So if you only select one polarization of light, which is the polarization that the disk is primarily putting out, you're cutting out almost all of the light from the star because the star has only got a small amount of its light that it's putting out at this polarization, but you're keeping much, much more percentage-wise of the light that you're getting from the disk.
Right. So what you're left with is the polarized light, which gives you the signature, the fingerprint, the shape, the detail of the dust and the stuff that's swirling around the outside. Hence these amazing pictures that have been released as part of this press release. You've taken away everything else, all the other bright stuff, and what you're left with is this detail, and it is very detailed.
Yeah, it's absolutely beautiful. So let's come back to the star and what this disk actually kind of is.
Okay.
So the star itself is called AB Aurigae. It's a fairly bright star. It's fairly close one too, I guess, in the grand scheme of things. It's only about 500 light years away from us.
Okay, that's not too far. That's all right. It's still a long way,
Yeah.
but you could get a lot further. Yep.
Yeah. So it's a type of star which is called a Herbig AE star.
Okay, what's that when it's at home?
Since I know you really like these.
Yeah,
these
no, look,
unusual names of
I learn something every time we talk, Emily, about the number of different possible things that there are. So let's add another one to the list. What was it again? A
Herbig AE star.
And that is a what?
So if you've heard of a T Tauri star, it's analogous to that.
I'm not sure that I have heard of a T Tauri star. So I'm not sure how far back we want to go in this. Well, if you haven't heard of a T Tauri star...
Have you heard of stars?
Oh, stars. Yes, we can start there. Let me ask you this. Is this a big star? Is it a small star? Is it a sun-like star? Is it... what? Give me something. Anything to hang on to.
It's a pre-main sequence star.
Yeah, okay.
Okay, we're going to have to go back. Again.
Remember, one of us is not an
so
astronomer here. That one would be me. So let's, pre-main sequence.
Yep. Okay. Going backwards. A main sequence star is, we call the main sequence kind of, it's actually an area on a graph, but it's much, much more interesting than just an area on a graph. The main sequence is the normal period of a star's lifetime.
Okay.
So this is its kind of ordinary state. It's when it is fusing hydrogen to helium and carrying on its merry, lifetime. So our sun is in its main sequence phase. It's, about halfway through its main sequence lifetime.
It's doing what stars do. Yeah.
Yep. And then after they finish up all the hydrogen and start doing all sorts of other crazy stuff, then they, become all these other evolved sort of stars. But what we're talking about here is a pre-main sequence star. So it's kind of, it's starry, it's collapsed down from its progenitor cloud of gas and dust. It's become something that's, it's switched on, it's become bright, it's now fusing, but it still hasn't quite settled down to its main part of its lifetime. It's still transitioning.
It hasn't got into its groove yet. It hasn't settled down and joined the sort of, late 20s into the 30s of the star's life where, you know what you're doing and you're just getting on with it. It's still in the turbulent sort of teenage years, early 20s. There's a lot going on.
Yeah, they're not quite adults yet. And they definitely are quite violent, these types of stars.
Yeah, no, that seems about right.
They put out a lot of ultraviolet light, for example, which is, fairly toxic to life. They're very unstable in terms of some of their surface stuff, so they often have flares and kind of do all sorts of slightly crazy things. The T Tauri type stars are maybe just the slightly more famous group of pre-main sequence stars, because those are stars that will eventually become what we call F and G type stars, G being the same as our sun. So they're kind of they will become sun-sized when they're on the main sequence.
But this wasn't one of those. So this star that we're looking at was a what?
A Herbig AE star.
Okay, so that's a pre-main sequence star. It's one of these sort of it's just warming up. It's still in its teenage angst years. But what else defines those? Okay,
so this means it's going to go on to become an A or a B star.
Okay, and that means?
Now means slightly hotter than the sun.
Okay.
So A stars are kind of, when they're on the main sequence, you're looking at between 7,500, 8,000 Kelvin, whereas our sun is around 6,000.
Okay, so teenage star going to go and become a hot, and that means that they generally have shorter lives, the hot ones, because they're burning through much faster.
Yes,
okay,
right.
So it's going to live fast, die young, and that's what we're looking at. Is the fact that it's a pre-main sequence, I'm assuming that that's related to the fact that it is still surrounded by this cloud of gas in which we are spotting this planet forming. That's all part and parcel. That you rewind the clock a bit, and you just had a big cloud of gas. Stars formed, and it's still very, very young. And now you're starting to see planets forming in the same gas. So this is a solar system in the very early stages, is what you're saying here.
Yeah. So the star's definitely less than 10 million years old.
Okay. That's pretty young by star standards.
Yeah, and we understand fairly well that stars and their solar systems kind of form hand in hand. They're all part of the same formation system, if you like. You can't really have one without the other. So yeah, the leftover kind of material from the gas as it's collapsed down into the star forms into this disk, and then it's kind of the things that happen in that disk which are related to how the star changes as it's forming, which go on to become these planets.
Okay, so that's the star, right? It's this star, this kind of star in this kind of environment. It's very early in its career. It's very early in the solar system's formation, or in its system's formation. Okay, so the planet then. What do we know about the planet? Does it look like a big planet, small planet? Is it close in, far away? What do we know?
All right, so let's look at the disk that it's forming in, right? So you can imagine a smooth disk that's kind of just uniform, like a dinner plate around the star. Now, that disk will very quickly, in the star formation, become perturbed by lots of different things happening. So it doesn't stay smooth for very long.
Yeah, smooth doesn't happen a lot in the universe, does it? Not really.
No. What does happen a lot are waves, right? Lots of waves. So in this case, we got these kind of ripples of shock waves that start to permeate out through the disk. And these are shock waves are set up by the star doing all sorts of, exciting things. And these form into the spiral structures, right? That are then that we see in these beautiful pictures. I think the ALMA telescope, the Atacama Large Millimeter Array that we've spoken about, went and observed this star in 2017 and spotted these beautiful spiral structures. And they go up to 450 AU from the star.
450. So that's 450 times further away from the star than the Earth is. That's what an AU is the average Earth distance.
Yeah, and then the Earth is from the sun.
Yep. Yeah. So, okay, so what's that in terms of, I don't know, our solar system then? How you go out to, say, I don't know, the outer planets, how many AU away are they from the sun?
So Neptune is about 30.
Right, and so these are going a very long way out indeed then. This is a very big gas cloud with lots of swirly stuff through it.
Yeah, and once you have these kind of structures, then obviously you want to understand not only the formation of those structures, but then try and see if there's any kind of distortions within them that might be, in this case, a hint of a planet. So the image that we'll put up in the show notes, obviously, because we're talking quite a lot about it, shows the structures out to something like 120 AU.
Which is a lot.
So they do extend more, but yeah, this is the bright inner region, if you like.
You mentioned the other images from a couple of years ago from, what was it, the ALMA telescope, was it? The ALMA Observatory?
Yep.
Which are not nearly as detailed. Those show some structure. There was clearly something going on. And I think back in 2017, they said, oh, look, planets forming probably. But this is a much, much more detailed look. Why the difference? What's the difference between the two telescopes that gives such a higher resolution here?
So a big part of it is the observing technique. So when you look in the microwave, it's harder to get higher resolution with longer wavelengths of light. And so microwaves are longer. They sort of tend to be a few centimeters in terms of the length of the wave. Whereas when we're looking in what we're looking at here, which is the near infrared, we're coming down to sort of micrometers of the length of the wave.
So that's the same principle that allows your microwave oven to keep all the cooking microwaves inside, but you can still see through the grill on the front of the door, because the grill has got holes in it which are so small that the microwaves don't even notice that they're there. So the microwaves can't see that level of detail, but the visible light can actually get through. The visible light does know that detail's there. This is a similar process.
Yeah.
That the microwaves that ALMA was using, they can show some detail, but the millimeter wavelength radiation that these new images are using are much, much more detailed. You can see down much smaller.
Infrared, yeah. So what we had those original spiral sort of images, and then what the astronomers did was they went away and looked at their models of how these structures form, and sort of started to think, okay, there's going to be a planet here, and we've got to make some simulations and show that this would happen in our simulations, and indeed the simulations were matching up very, very closely. And what they're seeing particularly is a bit of a disruption, a bit of a twist in these spiral structures. So if you've got the image of there in front of you, Chris.
Yes, I have.
If you look at where the star is, if you look sort of just below it, there's kind of a brightish sort of twist where it kind of joins two of the arms together. Do you sort of see what I mean?
Yeah, I can see that. So the image that I'm looking at, you can just see right in the middle. I mean, there's a big dark blotch, and I'm assuming the star is right in the middle of that. There's sort of a little ring that kind of looks a bit like, oh, there should have been something there that looks like it's been blotted out. But around that, there's the swirly structure. There's the various spirally arms. It looks like a galaxy. But then there's this bit which is very bright where two of those arms seem to merge. That's what I'm looking at?
That's what you're looking at, yeah. So this is where we think the planet is.
Yeah. Okay. So if you're looking at home, go and check your show notes, or just look down at your screen, because it might well be there in your podcast app, just showing right there for you to look at. Okay. So that's where we think the planet is.
So if you like, you can imagine those spiral arms are kind of the paths for the material to start to accrete into planets, to start to sort of come together. And so if you look where that twist is, that's about 30 astronomical units away from the star.
So that is sort of outer planet of our solar system kind of distance. That's sort of Neptune-y kind of region.
Yeah, that's pretty similar to Neptune's orbit.
Okay.
Yeah.
So does that tell us anything about what kind of planet this might likely be? Do we know enough about planet formation to know that?
We have some really good clues. So we're not 100% sure if the planet is formed already or if it's still forming.
Okay.
But we can say some things about from where it is and from its effect on the spiral structures, how big it is as well. So it's probably somewhere between 4 and 13 times the mass of Jupiter.
Between 4 and 13 times. So that's big. That's a big planet.
Yeah.
Hang on,
the small end of that scale is huge.
I just had to process that for a second. So, well, no, wait, that's even the little one is big. Wow. And I thought that Jupiter was already kind of classed as a big planet. It's not that far off being a failed star, really. So something of this size.
Yeah, it's
surely
pretty big.
At some point you sort of think, are you a planet or not? Is that on the upper limits of planet size, or is that just big?
It's not quite. I think you've got to go to something like 60 times the size of Jupiter before you start wondering whether it's fusing in its core.
So this is merely potentially an enormously big planet.
Just an enormously big planet.
Okay. Fair enough.
And maybe something like a 4-year orbit around its host star.
But looking at it now, and with all of this gas and stuff swirling around, like, would we be looking at, is that a planet in the middle of all of that causing all of this? Or is it's going to be a planet at some point in the future? It's still in the swirly phase. Whereabouts are we in that history?
So we've got that there's a lump of mass there. It's just kind of a bit unclear of how much it's formed into something kind of spherical that we would recognize as an independent planet, if that makes sense.
So it's on the way.
It's definitely on the way. And this kind of works really, really nicely with how we understand planet formation generally, because it is really these enormous planets that are reasonably far away from their host stars that actually form incredibly quickly and are the first kind of big planets to form in a solar system.
And why is that?
Yeah, and this is really interesting. So what happens when you take your disk in your solar system, then there's a really important point in that disk, which is called the snow line.
We've talked about this before, but you're going to have to remind me.
Yeah. So this is the distance from the star where water would freeze.
Right. Okay.
So close to the star, it's hot, so water is water vapor. Far away from the star, water freezes and becomes ice. So the snow line is the point where that happens. And so for our solar system, it's kind of somewhere about 4.5 or between 4.5 and 5 times the distance that Earth is from the sun, between Mars and Jupiter.
Okay, sort of around asteroid belt kind of area.
Yeah, a little bit further than asteroid belt. So probably better to describe it between asteroid belt and Jupiter. Now, the slow line is really, really important for planet formation because it tells you where the difference between rocky planets and gassy planets. inside the snow line, you're going to have rocky planets. Outside of it, you're going to have gassy planets. And there's really good reasons for that.
Yeah, I know you've explained this to me before, but that's intuitively not making sense to me, because if you have vapor closer to the sun and ice further away, then you got solids further away and vapor closer in. And so why do you get gaseous planets further away and solid planets? That doesn't make sense, Emily. Come on. So explain this one to me, as I'm being very slow today.
No, it's actually pretty complex. So it's complex, but it's interesting. So what happens is it's all about timescales, because you've only got enormous amounts of gas, so let's say particularly hydrogen and helium gas, in the disk for a few million years. And effectively 10 million years is your absolute cutoff when you don't really have gas in your disk anymore. Because what happens is the star it gets to the point where it's blowing all that material away. It pushes it outside of the solar system.
Okay.
It sort of, vaporizes it all. So you've only got this gas sitting around in your solar system for 10 million years. So that's the important thing to keep in mind.
Which seems like a very long period of time to us, but in planetary formation terms, it's not very long.
It's really the blink of an eye.
Yeah.
Right. It's not around for long. So what you've got to do is you've got to become big enough to hold on to a substantial... If you want to be a gas giant, you've got to become big enough to hold on to a substantial amount of gas, so that when the star starts to blow it out of the system, you can hold on to it, and it becomes your atmosphere.
Right. So it's not that. I see. It's not that smaller ones couldn't have formed. It's just that they wouldn't be there anymore. You've got to be a big one if you're going to last under those circumstances. Is that what you're saying?
You've got to be big, and you've got to be big enough to hold on to the atmosphere, to hold on to that. So, sure, you can have little planets form in the inner solar system, but they're only going to be little, and they're not going to hold on to this atmosphere. So if you want to be big and you want to get big, you've got to get big quickly, right? And the only way to get big quickly is to be beyond the snow line, because you've got ice out here. And ice is incredibly helpful because ice is very sticky.
Right. Now it's coming back to me. Yes. So explain to us again, why is ice sticky and how does that help?
So ice is quite sticky in the sense that if you have a little clump of ice and you stick some dust to it, it's attractive. It's going to stay in that lump. And it means that you can grow cores of material very, very quickly, as opposed to trying to stick two bits of dirt together or dust together, which are slightly harder to get to accrete.
Right. So as you say, if you want to grow big quickly, you want stuff that is going to tend to stick together and clump, and dusty ice is going to do that. It's going to do that really quickly.
Yeah, exactly.
But it'll only do that further out beyond the snow line.
Because that's where the ice is. Yeah.
Okay. It's all making sense now.
So you can grow these enormous cores very, very quickly. Within just a couple of million years, you can grow incredibly large planetary cores. And therefore, when you've got a substantial enough sort of core, you can start to hoover up all the gas that's around and hold on to that on the outside as an atmosphere. And then when the star sort of sheds the rest of the gas out of the disk, then you've got enough mass to hold on to the stuff that you've collected already.
Right. So after all is said and done, if you're big enough to hold on to it, then you stick around as a big, or in this case, a really quite substantially big planet. So when you said before that this one that has been observed is likely to be how many times larger than Jupiter? It was
maybe 4 to 13, a few times.
Would that be its end mass? Like after the star has said, nope, off you go to the rest of the stuff. That would be its final mass is, nope, I'm hanging on to this and I'm in the order of 10 times the size of Jupiter. That's what's left.
Yeah, that'll be most of its mass. Yeah, there's only very, very small changes from then on in. So if we look at sort of timescales, Jupiter's a really, really interesting one, and maybe slightly different anyway. But we know that generally giant planets can form at least a core that's 4 times the mass of the Earth in just about 3 million years, which is really
That is quick. That's very, very quick. And for contrast, the smaller rocky planets closer in, how long do they take to form?
They take ages. So because you don't have this ice, you're just slowly accreting, dust with dust and dust and dust, and getting dust up to the size of, say, sand, and then you're sticking the sand together, and then you're getting lumps of maybe the size of a car, and then you're sticking them together. It's a slow process.
It's a very slow, patient process to build up a rocky planet. But the gas ones, like that.
Yeah, so that can take hundreds of millions of years for these smaller rocky planets to form. And we can tell that today because if you look at the atmospheres of all the planets in our solar system, you look at the atmospheres of the giants, then they've got mostly hydrogen, a bit of helium, because that was all that was around at the time, right? But if you look at the atmospheres of the inner planets, well, they're really interesting and really diverse, but they're definitely not mostly hydrogen. If we had a mostly hydrogen atmosphere, we'd be a bit pooched, I think.
We'd be in trouble. But explain that. Why? Is it just simply that you've had more time for these other materials to build up, or why do the rocky planets?
So we have secondary atmospheres for the terrestrial planets, the rocky planets. So we had a primary atmosphere at one point, which was the hydrogen and helium, but that got stripped away by the early sun, leaving again just a lump of rock. So then we had a secondary atmosphere form. In the case of the Earth, this is formed from outgassing, a lot of geological activity and outgassing, as well as things like comets hitting the Earth and vaporizing. So they've come from other places, basically, the atmosphere.
Right. So it's not just what you managed to gather along the way. There's all sorts of other processes that are saying, all right. We lost that first atmosphere. That was careless. But we've got this one now. But it takes a really long time for those processes to kick in and say, here is planet Earth, here's your atmosphere, well done. You can have this one now.
And that's why even Earth and Venus have quite different atmospheres, because their origins are quite different in the sense they come from different planets.
Very cool. Okay. All right. So wrapping all of this up then, we have some quite extraordinary images of a star a long way away, but not so far away. What did you say it was? Something like 500 light years?
Yeah.
Okay. So that's close by some scales, but we have these amazing images of the cloud of gas around this very young star, proto star, pre-main sequence star, in which is
her big AE star.
Yeah. Drop that at your next cocktail party. And in these gaseous disks swirling around, there's a twist. And that twist is showing that somewhere around the same distance as the orbit of Neptune in our own region, there is a massive planet in the process of being formed, which is very cool. It's cool on a number of reasons. Number one, because we can actually see it. These images kind of look like they're someone's imagination, and they're not. They're real. Someone took this picture, and that's awesome. But number two is, presumably, Emily, this is teaching us actually quite a lot about planetary formation, and in particular, the really interesting dynamics of the biggest planets within a system. I mean, in our own, Jupiter is the biggest, and it's the biggest by quite some margin. So, I mean, are we learning a lot about Jupiter-y type things?
Absolutely, yeah. I mean, if you were to think about our solar system, it's kind of weird that Jupiter is this biggest planet. And coincidentally, or maybe not so coincidentally, it also happens to be the largest gas giant to this snow line, right, that we have in our solar system.
The closest one.
In fact, very, very close. It's Jupiter's at 5 astronomical units, which is really only just outside of where the snow line is.
Right. Okay. So you're kind of saying that with a bit of a sense of, well, that may not just be coincidence. The fact that the biggest one is just there, just in a nice position just outside the snow line to be taking greatest advantage of that.
Yeah. So there's a couple of processes that we think might have happened that meant that Jupiter kind of had a leg up in terms of formation and growth and becoming the biggest planet.
Okay.
But just purely by its location. So there's some models that suggest that Jupiter managed to grow to 150 times the mass of the Earth in only 100,000 years.
Now, we've already decided that on these kinds of timescales, these sorts of processes, millions of years is already very, very quick. So growing to that size in hundreds of thousands of years is extraordinarily quick.
Yeah, 100,000 years, that's like dinosaurs, right?
Exactly. Not even dinosaurs.
That's crazy.
Not even, like dinosaurs are millions of years ago. So this is sort of,
Yeah.
proto-human evolution stage. That's really quick.
Yeah, crazy. And this is about half of the mass of Jupiter, right? Today it's about just over 300 times the mass of the Earth.
So it grew fast.
Yeah, really fast. And we think this is, two different things that are happening to help Jupiter, if you like. So first of all, it's quite close to the snow line, which means that you've got kind of a bit of evaporation going on. So that means that the water or the ice that strays too close to the snow line, or if there's a solar burst or something like that, which means there's a temporary warming of the inner parts of the freezy bits of the solar system, then you get evaporation, which means that when water evaporates, it changes the pressure in the area around it. So you get sort of pockets of low pressure, which help to kind of draw material into regions faster. So you've got pressure changes. Basically, you're accreting things into clumps easier.
Right. So being close to the snow line means you've got that change of state, which just happens to be a really good environment for going, hey, clump even more so. Come on, come in. Let's make something big.
And the effect of that is you get this kind of pile up of dust just down the outside edge of the snow line. And that pile up of dust means you've got sort of a higher density of material than you would even just, a couple of astronomical units further out. And so Jupiter is able to scoff that all up and become huge.
Yeah. Nice one, Jupiter. Meanwhile, Saturn's a bit further out going, well, I guess I can't be that big, but I'll just have rings. I'll be special because I'll have rings.
Since when has Saturn ever been annoyed at any of the other planets?
I don't know. It might have a size complex. You don't know. No one's ever asked.
Oh, Saturn's the darling of the solar system. It couldn't possibly.
Yeah, but have you ever asked yourself why Saturn feels the need to be so ostentatious? Have you ever asked yourself that? No one's ever asked poor Saturn why it feels the need to be so out there. And it's because, I'm telling you, it's because Jupiter is just so big and Saturn's got a complex about it. That's what it is. I reckon astronomical psychology, it's the next big thing. Trust me on this one.
I wouldn't like to go anywhere Neptune because, that planet's just... half of the people in the world probably forget it exists.
Yeah, and even the pictures of Neptune are a bit sort of... Is there much going on here? Can we see any surface features? No, it's just sort of a bit it's a bit kind of smooth.
Bit blue.
Yeah, a bit smooth and blue. And no, Neptune's kind of the middle child. It's sort of a bit forgotten, and it's, well, I'm just going to go and do my own thing then. That's fine. I'm just over here being blue.
Yeah, and it didn't get a, slightly humorous name like...
No, we'll leave that one alone. Astronomical psychology. Yeah, maybe not.
I do, yeah. So, one last thing you can say is, what's next? What's next for this?
Always the good question. What happens next? What have we learnt from all of this? What do we take away? What do we apply next?
Well, the good news is that despite global pandemics, we are still building new telescopes and pushing ahead with new projects. The big next one for this particular system and others like it is going to be the ELT.
The ELT, is that the extremely large telescope?
It is indeed.
As opposed to the overwhelmingly, the owl.
You were hoping that guess was going to be wrong.
No, I was trying to remember. I was also trying to come up with something funnier as well. Yeah, but it's not the overwhelmingly large because that got cancelled, and it's not the ludicrously big. It's just the extremely large, which is, big, let's be clear, it's a very big telescope.
It is 39 meters in diameter, the mirrors on the extremely large telescope. Compare that with our largest optical telescope currently, which is 11.
Yeah, so it is extremely large. There's no doubt about it. And that's due to come online when?
Maybe 2025.
So not far away.
We're still hoping for.
Not far away. So that'll be cool.
Very cool. And so we think that with this enormous telescope, we'll actually be able to resolve the gas falling onto this planet.
Seriously?
Yeah.
Wow.
So we will be able to say that little stream of gas that's still going onto the planet, or indeed if the planet's kind of stopped and it's
that's
kind of off on
nuts.
its own.
That's so cool. I mean, if you look at the difference between 2017 with the ALMA pictures, which is, hey, look, there's some interesting structure, to 2020 at a different wavelength of the light that we're looking at. It's the infrared versus the microwave. But the structure that you can see and the detail you can see is just, wow, check that out. 5 years' time, we're going to be able to see at the level of detail of, no, this is the gas that's actually accreting down, falling down onto the planet itself. Really? Wow.
It's amazing. And this is within living memory of professional astronomers thinking the idea of imaging a planet outside of our solar system is bonkers.
Yeah, good Lord. I mean, within a not even a hugely long lifetime of seeing the first exoplanet at all in any way, shape or form, to why don't we just point the telescope at it and actually watch it form, in real time. That's not bad. Well done.
I think it's amazing.
Well, that brings us to the end of another edition of the Syzygy podcast. Today we've been talking about big planets. Emily, I don't know, every time we talk about this stuff, I'm still absolutely gobsmacked that this is a real thing. And it's a real thing that people do in the world, is looking at, finding and learning about exoplanets. It feels like that should be science fiction, and it's not. It's real stuff. It's very, very cool.
Oh, it's an absolutely fantastic career to go into. I mean, not that I do exoplanets directly, but I can highly recommend.
You can highly recommend.
It's a flexible career. It works in even lockdown. You can still continue doing your observations with Space Telescope.
You're saying if you go into exoplanet hunting, you're basically securing your job for life, because not even a pandemic could take you down. I think that's very good job advice. Emily, if people wanted to get in touch with us, if they wanted to ask some questions about exoplanets, or indeed get some career advice from someone like yourself, how could they possibly, in any conceivable way, get in touch with us? Surely it's impossible.
Oh, no, but it turns out we've got the internet. It's
all
good.
Thank goodness for that. So how do people find us?
So we're on Twitter. We are at SyzygyPod, SYZYGY pod. Same thing on Instagram, and same thing on Facebook. And you even have a spectacularly gorgeous, I would say, and I can say this because I had nothing to do with this creation, website, syzygy.fm.
Yes, and you can... News,
links, pictures.
All of those things. You can go to the contact page. You can send us a message, as people have done from time to time. And when we get a question or an interesting idea through, we will address it on the show, and we might even turn the entire show over to answering some of those questions. You never know your luck. So get in touch. Go and check us out on the social medias and come and say hi. If you want to help the show, there's a bunch of ways you can do that. First of all, spread the word. Tell everyone you know about the show. Tell them where to find us, syzygy.fm, or their podcast client of choice. We're out there. We're on all of the usual lists. Other ways you can help the show, you can go to our Patreon, patreon.com/syzygypod, to financially help us keep the lights on, the website running, and the electrons flowing through this wonderful thing that we like to call our podcast. But even if you don't do that, just keep listening, because we're going to be back again in about a week or so's time for a bit more astronomically flavored goodness. Until then, Emily, stay safe, stay warm, and I'll catch up with you in about a week or so.
See you later.
All right. Bye, everybody. What's the latest on James Webb, by the way, speaking of only 5 years?
Oh, that's a good question. It's probably been delayed.
Yeah, but at least this time they've got an excuse. So, it's coronavirus. Everything's been delayed.
I think my best NASA lockdown story is that I honestly don't know which mission briefing meeting it was in, but there was official guidance for NASA employees working at home who were therefore, in remote control of, say, rovers on Mars. There was direct guidance about having their cats in the same room with their keyboards open and being very, very careful to not let the cats start to control spacecraft.
That's fabulous. That is so good. That is so good. You can imagine someone in a meeting at NASA just going, I think maybe we need to talk about the cats. I don't know. I just had this sense that something could go horribly wrong.
Curiosity's just driven itself off a cliff. What?
It's not just someone sending a weird email to someone. It's, we just drove a rover into a wall. Sorry.